We have a really interesting problem here with this question. So there's a little sports car, 970 kilograms, is going to slam into the back, moving at some velocity to an SUV of 2,400 kilograms at rest at a stoplight. So you can imagine that idiot that's on his phone, he's texting, oh shit, I hit the car in front of me. The car moves 2.4 meters. I kind of just drew it as a block here of the combined mass, which is, I'll give you this, 3,370 kilograms. And we're told that the kinetic friction coefficient is 0.80. So we have to use the idea to find this velocity that momentum is conserved, right? Momentum initial equals momentum final. But before we do that, we need to know the final velocity. We're not given that, right? We need to know what the final velocity is. And remember, this is an inelastic collision, so we can treat a perfectly inelastic collision. So they lock up and their masses are combined and they move with the same velocity. So we're allowed to combine it here, just not here. So before we actually get into that, let's find the momentum of the coupled cars together. But how do we do this, right? We need to use the idea of work. And before we get to that even, let's define with a free body diagram what's acting on our car or our coupled cars. So the cars are connected together. There's their weight, mass times gravity. There's the normal force. There is the force of friction. And then there's that overall force pushing them that way. So this is, we'll just call this force of A. Okay, so to find the force of friction, we need to know the normal force. And we can get the normal force from the weight. So notice we're going around the circle here. The mass times gravity is, let's see here. So 3,370 kilograms times 9.81 meters a second. We get the weight to be 060 newtons. This means that the normal force is same in magnitude, and I'm not going to use relative values here. I'm just going to use their magnitudes. Friction here will be equal to, so the force of friction is going to equal our friction constant times the normal force. So we take 0.80 times our normal force here. We're going to get that the force of friction equals 26,448 newtons. Okay, pretty simple. What can be said about that overall force? Well, friction is the thing pushing them, right? So we can say that the force of friction is equal to the force of A. So we will say that the force of A here is also equal to this many newtons. So now that we have newtons and we have distance, what does this sound like, right? It should ring a bell as maybe the last thing that you've learned. And I'm going to get rid of this momentum part here. Well, it should be noted that work equals, what does it equal? The parallel force times our displacement. Okay, and we have force, the parallel force and displacement. Force of A, displacement. So we can say that this is equal to 26,448 newtons times our displacement of 2.4 meters. And when we times it together, we'll get a Newton meter, which is a joule, which is good because we want work. So 26,448 times 2.4 meters is going to give us an overall work. Jeez Louise. 63,475 Newton meters. So we have our work, and there's another thing that you have to catch on to is that this work that's done to push the car 2.4 meters is the overall work, right? The car's not moving in the Y or Z direction. It's literally just moving in a linear straight path 2.4 meters from its origin, right? So we could say that this is actually work net. And what do we know about work net? Well, work net is equal to kinetic energy plus potential energy. Alrighty, or sorry, change in kinetic energy plus change in potential energy, right? But potential energy isn't really there, right? Because we're not changing our y component based on a force like gravity, right? A non-conservative force. So we can say that the work net equals KE, right? And KE is 1/2 mass velocity squared, okay? So we can actually find our velocity here if we just have the mass. So let's do that. So V squared, or sorry, before we do that, we need to back up a little bit. We need to say that the work net is equal to that term. So work net is equal to this. So let's write that out, 63,475 Newton meters. I could express it equal to kinetic energy, right? Because work net equals kinetic energy in this case. Or you can write it as 1/2 mass velocity squared. And we'll do that, 1/2 mass velocity squared. We can plug in our mass. So let's go ahead and do that, 63,475 Newton meters. So 1/2 mass, 1/2 of the mass is 1,685 kgs, velocity squared. Okay, let's divide by our kilograms, 475 divided by 1685. We're going to have our units. We're going to have 37.7 meters squared second to the negative second, right? Because a Newton meter would be a kilogram meter squared per second squared. So when we cancel out the kilograms, we're left with those units, equals velocity squared. We take the square root. Our velocity will be equal to 6.14 meters a second. Okay, so the car after impact is moving at this velocity here. So now, and we'll call this V sub F, final velocity. Now we have, we need to find the velocity of which the sports car was traveling. So we can actually go ahead and do that. We just need to know that momentum is conserved in a collision, okay? This is a perfectly inelastic collision, so we'll see why that's important in a second, but let's define momentum initial first as our mass of the sports car, and we'll call that MS, velocity initial, plus the mass of the SUV, so we'll call that SUV, and the velocity initial of the SUV is equal to, and notice how they stick together here, so we can treat their masses as the same. They're one body now. They're not separate bodies. We don't have to expand it to two terms. We can just collapse it into one. So we can say that the mass of both, so we'll just go M in this case, is equal to velocity final, or times velocity final. So let's cancel out some terms here because that's physics. The mass of the SUV, okay, 2,400 kilograms. What's its velocity? Well, it's 0. And what happens when you multiply something by 0? It just drops out. So this actually cancels, right? The mass of the SUV times 0 is 0 Newton meters, right? So, or sorry, Newton seconds, geez. Okay, mass of S times its initial velocity. So we have 970 kgs times the initial velocity of the sports car is equal to the mass of the overall body times velocity final, which is 6.14 meters a second. Okay, let's do some simple math here. Let's multiply these together. And let's divide by 970 to get an initial velocity of 21.3 meters a second. And that's how fast the car was moving to slam into the back of the other car to make their combined mass move 2.4 meters, given a kinetic friction constant of 0.80. So yeah, hopefully this answer made sense. It's quite a long problem, but I think it's a really, really good one. on. It makes you think, it makes you connect back to the work, given that this part here, it moves 2.4 meters. This is actually what they use in the police force. So I hope you guys enjoyed. Have a wonderful day.